Hello folks, this is CIS 2353 again, and it is week 6. We are going to cover linked structured lists this week, and the chapter reading is chapter 7. So let's get started. Don't let the number of slides scare you. They actually break up the code quite a bit. We'll be going over the code. I've pre-typed pretty much all you need for the chapter, and I'll be uploading that as well. So this chapter is on linked lists as opposed to array lists, which we covered last week. So a linked list is a list object. In other words, it's an object in a class, or object of a class rather, that implements the list interface, in which the following property is satisfied. Each element is contained in an object. So every element that lives in the list is an object, and this object is called an entry object. In some languages and in some contexts, we call this a node that lives in the list, N-O-D-E, node. This object, though, this entry object, also includes a reference called a link to the entry object that holds the next element in the list. So for example, when we first have our list, there's nothing in it. But when we create a single node, we get this, the head of the list. We will have, well, we'll say this is the beginning actually. Let's pretend these two nodes aren't there yet. We just have Kazi over here. Well, when Kazi's added to the list, it's the first item in the list, and it has a next pointing to null. It's not actually, it has no next. So when you add another item to the front of the list, though, that item gets created in memory, and then a link is created to the current head of the list, which is Kazi, but now we want John to now become the head, so then we set the head equal to this node. When we want to add another node, let's say we want to have Eric in it, we create that node over here, and then we set its next to the current head, which is John, and then we set the current head to Eric. So each of these items points to the next. This is very different from what we've experienced with arrays and array lists, because in this scenario, what we've got going on is the list is linked between each item. Each item is responsible for ensuring that it points to the next item in the list, rather than contiguous memory. Okay, so the memory in a linked list is not contiguous. If each entry object also includes a link to the entry object that holds the previous element in the list, we have a doubly linked list. So this one's a singly linked list. You only have each element pointing to the next. But if we have links pointing to the previous element, in other words, each of these nodes or these entries has not only a next but a previous, then we call this a doubly linked list. The beauty of a linked list is that insertions and removals can be made without moving any elements. Only the links are altered. The problem with an array example is that, or an array list, is that if you want to add an element near the center, even though we may not be directly doing this, the implementation behind the scene has to move all these elements out of the way to make room. With a linked list, the removal, for example, or insertion, is a lot more simple. So to remove the entry John, let's say we want Eric and Kazi to be in the list still, but we want to remove John. You might think, well, if we remove that, then Eric will break off over here and fly into space, and then Kazi will break off over here and fly into space, and the list will be lost. But really what you do before, all you have to do is set Kazi's previous. If it's a doubly linked list, you set Kazi's previous to John's current previous, which is Eric. So you're bypassing John. Okay, Kazi no longer points to John like it did before. And then Eric's next no longer points to John, it now points to Kazi. So now there are no references pointing to John, so the garbage collector will come by and pick it. So it's no longer part of the list, even though you see that John maintains links to Eric and Kazi. It is actually no longer part of the list. Because it's not fully integrated with the other list elements. There may be an arbitrarily large number of elements over here and here as well, and we've just removed an element without destroying the list. So this chapter is devoted largely to the study of the linked list class, which is a doubly linked data structure, and it's part of the Java collection framework. However, as a warm-up to really understanding this, they create they call a toy class, which is a singly linked list. So the first thing that we're going to do, we can look at how it's used inside of Eclipse. I've created the singly linked example. Now, it does not match the one they use in the book, although the one they use in the book would work perfectly fine with our singly linked list class that we've created that I'll show you. But the singly linked list example here, basically I just create a list, singly linked list of strings. This is not provided by the Java Collections Framework. This is a class that we're creating ourselves. And then we call a method called add to front. And then since I'm making this link specifically of strings, I'll add Bob, then Sam, then Sally. And then I'm going to iterate through it using an enhanced for loop. So for every string in this list, I want to print it out. So if I run it, you notice it'll print out Sally, Sam, and Bob. So it prints out in reverse order. Sally was actually will actually be at the front of the list, because when you initially call add to front, Bob will be the only element in the list. So if you think of our diagram where we have our rectangles with the links and everything, you've got Bob sitting there. When you add Sam, Sam becomes the new head of the list, or the new front of the list. Then it points to Bob, and then finally Sally will be added to the list, and then Sally will become the new head and then point to Sam. So this is not doubly linked, so we only have to worry about the single link, the next link. Now you might think, well, how are we printing it out using an enhanced for loop? Well, we've created an iterator, which we'll talk about in just a little bit. This is the definition of our singly linked list. We extend to abstract collection, which is also a generic. So you have the placeholder element E here that basically means, and you also have to remember to put it here as well, that basically means we can make this list of any type. This is just a placeholder, so we can create a singly linked list of strings like we did here, and then that will take the place of our E. It's a type parameter, and also we implement list E as well. So we can make it of strings, of any of the wrapper classes like integer, character, Boolean, all capitalized, of course, because those are wrapper classes. You can't use primitives because it expects an object to be here, so you would have to use the wrapper classes if you want to, say, make a singly linked list of ints. You can't say singly linked list int because that's not a reference. So what does the constructor do? Well, the constructor, well, I guess first we should say that we have one field here. This is just the head of the list. And this is of a type entry. Now, we'll talk about the entry in just a second. Entry is a type in and of itself as well. We've created it as an inner class later in this public class here. We have a protected field called entry. That's the head of the list. So that basically, this is a special pointer that this singly linked list keeps track of. It points to the front item in the list. And you might think, well, what's inside entry? Well, they show you over here, and we have it later. I've put it below the public, well, below many of the methods in the class definition, but you've got a protected element of some type, E, and then you've got a link to the next item. That's all we need for a singly linked list. You just need the element that's living at that particular entry, and you need a next pointing to the next element in the list. Okay, so they put the protected class in there, and as we see here, I'm going to show you near the a little bit before the bottom here. You've got the entry class right here. You've got protected E element and then protected entry E next. So it's a protected inner class representing a single node in the linked list. Now some of you might be thinking right now, well, I thought you could only have one class in a file and it had to have the same name as the Java file. Well, that rule only applies to public classes. You could only have one public class inside of a file, and the file has to have the name of that public class. You can, however, have, for example, protected inner classes, such as these. There are two here. There's one called the singly linked iterator, which is what we implement to allow the class to allow objects of the class to be iterated through using, for example, the enhanced for loop that we have right here, right? The range-based or enhanced for loop would not work if there was not an iterator defined. Okay, so we had to define an iterator type. But we'll talk about that in a second. So next up on our agenda here is our constructor. The constructor initially sets the head to null. There are no elements in the list, so the head is null. Null is just a special value, meaning there's nothing there. It's not pointing to anything, so there's nothing. Now, how do we know if it's empty? Well, we create a method called isEmpty. Well, how do we define that? It's going to return either true or false, and what did we define an empty list as? Well, if the head is null, that means the list is empty. So we just return head equal null. So is equal to, we use the equality operator here. If the head is null, then it will return true if it's false, or if it's not null, meaning it's a valid memory location, it will return false. The next thing we might be interested in is add to front, right? Because we added Bob to the front initially. Then when we added Sam, Sam actually took the place of Bob, and then Sally, even though she was added last, is now the head of the list. So as you add the items, they're actually put in the front. So that's why we get the printout Sally, Sam, then Bob. Going back to here, to add an element to the front of the list, we have the element here passed in as a parameter. You create a new entry first because we have a new element we're trying to add to the list, but it's not wired into the list yet. Now then you set new entries element equal to the element you're trying to put in its data, okay? And then you set new entries next equal to the head of the list. This is where you wire it into the actual list. These two just create the element and set its data. It has nothing to do with the list. You could independently create an entry yourself, and if you had access to it, and you could do pretty much anything with it as a standalone item. But that's not really what we want. We want to actually put it in the list. So you say next, or new entry dot next equals head. So what does that do? In this example from earlier, let's assume we're adding Sally. We have Bob and Sam already on the list. Sam is the next, it's the current head actually. So Sam is actually the current head now. So then when you are adding this element Sally, you've created it, you've set the data. You say basically the Sally node's next equals Sam. Then what do you got to do? You have to make Sally's node the new head. So how do we do that? You say head equals new entry. Now these two lines might look a little bit squirrely because it looks like you're just using the same head here, but remember, you're using the old head here, and then this head is just a pointer to it's a pointer to the front of the list. So we want this new entry we just added to be the new front of the list. The reason we do this, where we say new entry.next equals head, is because we don't want to lose the rest of the list. So even if this head points to a list that has 100 items in it, when we add a new item or a new new element to the list, then you say head equals new entry, that will add that element to the very front. Well, what about size? Well, we don't have the luxury of just being able to say array.size because we don't have an array backing this. There's no way to access, do random access on the elements. Okay, so that is a downside of using a linked structure for your list rather than the contiguous array. However, there is a way to find out the size. You just go through the list and count it. Okay, we're going to kind of do a couple of this and we'll come back to the size in just a second. They give you some of the definitions, or at least the declarations. Okay, when they get to the size, they make a kind of a good point here. They show you how add to front works. The head, again, is the pointer that points to the specific items, and then the last item in the list just has null as its next, so it's not really pointing to anything. Okay, so size. Now, how do we determine the size? Well, they use a for loop. Okay, I did not use a for loop, but this is equivalent to what I've written, and I'll show you what I've written as well. So this right here, public int size, they have a count, and then they return that count at the end. They say for, they initialize, or they use an entry to point to the head. You don't want to use the head itself, because then you're destroying the list as you move along, because ultimately you're going to set the item equal to the next item. So you don't want to say just, head equals heads next, because then you're destroying the list. That's how you would actually destroy the list. So how do we do it? You have to create another reference here, a pointer. Essentially a reference that points to head, contains the memory address of the head currently, but head doesn't change. You don't change head in this, so this is a non-destructive move. You say as long as current is not equal to null, so this is your loop continuation condition here, current not equal to null, current equals current next. So what are we saying here? We're starting at the head of the list, going until we get to the very end of the list. Remember that the last element in the list will have a next pointing to null. So ultimately, when we say current equals current next, that will cause us to eventually get to this null value. And then you would break out of the loop. What are they doing in this for loop? Well, this is the body of the for loop. They didn't use curly braces, but since it's only one line, you can just use the single statement, or one statement, you can use the single statement. So count plus plus, that's all they're doing. They're counting the items in the list. So traversing it and counting them. I used a while loop just because it is a little bit cleaner for this, because the other one's not really a count controlled loop. It's a sentinel controlled loop, even though we're doing counting. So it seems to me that it makes more sense to use a while loop, but that's just me. It's a matter of style. It does not matter if you use the for loop or the while loop. So we do the same thing. You initialize count, you set the current equal to the head, and as long as or while the current is not equal to null, increment count, and then set current to currents next, and keep going until this is true. So when the current is, when this is false. So when the current is null, it'll break out and then return count. So if you have 5 elements, it'll go 0, 1, 2, 3, 4, which would, if it were an array, or just 1, 2, 3, 4, 5. Ultimately, the count is going to be 5 in that case. So with an array, you wouldn't have to count. You just say array.length. It knows its length. It keeps track of it. Everything's fine. It's contiguous memory. You don't have that luxury in a singly linked list, because every time in add to front, when you create a new entry, the memory is not guaranteed, and probably rarely so, contiguous to the previous entry. They could be all over the place because they're dynamically allocated. Okay, so the next thing, they have contains. I didn't implement that in my implementation. You can fill it in really easily. It's not very difficult. I don't think I oh, I did. Okay, I guess I did implement it. All right, so I did this not that long ago, so I should remember this. But public Boolean contains. You have an object here. I again use a while loop instead of a for loop. So I set the current equal to the head, while the current's not equal to null. If ever I do find that object, okay, however equals is defined for that particular object. So if I pass in, a string or a whatever, and I say dot equals current dot element, then it's going to return true. Otherwise, if I get through the whole loop and I never find one that matches, I will return false. So in this particular implementation, it's going to determine if we find an object that matches this object. In other words, is the same object, is the same memory location. So that's basically how we're defining equals for our object that we pass in. So no matter what it is, it's going to call this. And then we have Iterator here. This is so things like our for each loop, it calls this behind the scenes. Or if we wanted to explicitly obtain an iterator, we could call this. We could say, our singly linked list named names.iterator and get an iterator. So we have to be careful though. What are we doing though? We're returning an iterator to this singly linked list, and that actually happens to be another class. Okay, so this is a class that we have to define in order to allow for iteration across our class using the pre-described or predefined techniques and methods. So here's another inner class below the entry class that I've written called SinglyLinkedIterator class. Establishes a convenient way for the user to loop through the elements in the, or access the elements in the singly linked list objects. So it's another protected class. Notice it's not public, okay, because you only have the one public class. Protected class SinglyLinkedList Iterator, so it's a different class name, implements Iterator. So this is what allows us to be able to return this as an iterator, because this should return an iterator. Any calling class expects this, or any calling object or calling client of the object would expect this to return something that implements iterator. So it's a quote-unquote iterator object. So how does this work? Well, they do expand it in the book, but I've just started it the way they do it throughout the book. Rather than in the problems, you've got a next, that's all it is. And at the very beginning, you set next equal to head, so that's actually the first element in the list. Now, where did head come from? I don't see head defined in here. Well, since this is an inner class, it has access to any of the outer class's items directly. So next equals head, that's pointing to the head of the list that's containing this class. So that's kind of clever. Then we say public boolean has next. Well, as long as next isn't null, it has a next. You've used has next probably in a lot of different scenarios, maybe with the scanner class or other classes. Has next is used very frequently. So that's because those classes that you're using that you have has next from have an iterator. Now what about obtaining the next? Well, this returns E, whatever E is. Could be a string, could be a person, could be a horse, could be a scanner, could be a cow. You have E here, and it returns a next element. You say E, the element equals next, which is whatever, I know it's kind of a strange name, but whatever the current element is. Maybe you could rename it current or whatever, it's fine. But you set it equal to next element, then what you do is you progress, because you want to set next equal to next.next. That looks really, really funky, because there's a data member in entry, if you'll recall, named next also, but that's perfectly legal. There's no confusion or ambiguity here. It just looks kind of funny because we're not used to it. Is this next referring to, or what is this next referring to? Well, it's you can see as I hover over it, it's referring to this guy right here, right? So I'm qualifying this name, so it knows that I mean the member named next, not the element here. And then remove, I didn't implement. So you could find a way to implement it. It wouldn't take very long. So that's pretty much it with this guy. So that'll help you maybe understand the doubly linked list. So we'll go through a few more and just to make sure everything's understood a little bit more clearly. So an iterator is an object that enables the user to loop through the collection without accessing the collection's fields. And that's important for data hiding. Okay, so implementation hiding, or what some people would just simply call information hiding. It's an aspect of object-oriented programming. So the iterator helps you move through the collection without accessing the collection's fields. Okay, so they implemented a little bit more on that, but then you've got the linked list iterator. Next method returns the element whose entry the iterator is now referencing, and then advances the next entry. So that's actually exactly what happened right here. We say that the element equals the currently accessed element, and then we set that to the next element in the list, and then return the currently accessed element that we had obtained. Okay. So there's your iterator. It's just showing you how to iterate. You can go through each of them. So right. So you need to save the next element, advance next, and then return the saved element. So we did the implementation already, so we're not going to belabor that. Okay, let's see what else we got here. Okay, the doubly linked list class, linked list of E. This is actually the one that is provided for you in the Java Collections framework. So this is the one that you're probably more concerned with. You're not implementing this. This is already provided for you. So for the most part, the linked list class has the same method headings as the array list, which you've already dealt with. But those classes have some different estimates for some methods as far as time is concerned and such. So, for example, get and set in the array list, get and set are constant. In other words, you access it directly. It doesn't matter if the array list has 1,000 items in it or 10. It can be accessed. The items can be accessed by getting them or the element set at a particular index immediately. Doesn't depend on n, in other words. Because the memory is contiguous, behind the scenes they're doing a little tiny bit of math, and they can determine based on the initial memory address where is element 15. Okay, they just basically take 15 multiplied by the size of each element, and they can go to the next element very easily because the memory is contiguous or adjacent. Memory locations for each element E or entry are right next to each other. You don't have that luxury with the linked list because, as we pointed out earlier, when I did a count, you have to actually move through the whole list to get to a specific item. If you want to get an element at in the list, it has to actually move down the list and count until it gets to the quote-unquote index that you want to access. That's why its worst case is linear in n rather than constant like it is with an array list. So its worst case is linear in a linked list implementation versus constant for an array list implementation. Sometimes, though, the linked list versions are faster. So, for example, add, if you add a particular element, the worst time is constant versus linear in the array list object because of the possibility of resizing. The array list has to possibly resize and then copy over all the elements to add a new element. So if it gets too big, the array list has to create a new object or a new array, basically, and copy all the elements over and make that the new array. So that's actually takes a longer time potentially with the array list, whereas with a linked list, all you have to do is move down the list where you want to, or well, not move down. In some case, you might have to move down. In some case, you might have to just put it at the beginning, which is what we're really talking about. This adds it to the front, so you'd basically just plop it there and you're done. Basically, to get to a particular position in a linked list, that takes linear and n time. But once you get there, you can remove or insert in constant time. That magnifies the importance of iterators because once an iterator is positioned somewhere in the collection, you can insert or remove in constant time. Here are the method headings for all of the methods in the linked list class. There's quite a few. Okay, so there's a couple constructors, add, a couple overloads of add all, add first, add last, clear, clone, contains all. There's a lot. Okay, get and set and everything, equals. So, of course, our friend toString, but set, remove, those are all very, very common things you would do with a list. We're not going to go through the whole process input thing, but all they're doing here is they're just showing you a little bit about how we can add items to a linked list. So you can use it pretty much the way we were using our SinglyLinkedList, except they've actually called remove and implemented, obviously, and then set as well. They've done that. So it's pretty simple. Okay, so they're showing you the list iterator. I'm not going to go through the whole thing. Just know that it comes with a list iterator as well. It's just called a list iterator. So if you need to access that directly, and you're not just using a for each loop, or I'm sorry, an enhanced for loop, then you can just actually create an instance of a list iterator with whatever type the list contains. So this actually has to match the type up here as well. Okay. So an empty linked list, what does that look like? Well, it'll keep track of the size as 0, and then every time it adds an item or removes items, it keeps track by incrementing and decrementing behind the scenes. But it's pretty simple. You've got the header pointing to the head. It's essentially the same thing. The header and the head pointing to an individual element here. The element is set to null. The next and the previous are both pointing to itself. So whatever this header element is. Okay, the element's null, but the entry itself is not. So a linked list with one element, you have this is actually counted as the single element. This is just a kind of a dummy element at the front. Significance of the header entry is that there is always an entry in the back of and in the front of any entry. That simplifies insertions and removals as well as iterations. So you'll notice that when we get to the ending element, its next does not point to null itself. It points to this header element. Okay, so this header element that actually it has null as the element that lives at it, but the actual entry, sorry, I should be saying the header entry. This header entry doesn't count as an element of the list, but it's used as a good thing to point to. Okay, so Eric points to that, and then Betsy can point to previous. So they're all pointing to either a next or a previous, and it makes it a lot easier when Betsy gets all the way over here. How do I get back to Eric? Well, you just have to take null's previous, not null's previous, but this element, the header's previous, to get back to Eric. So it's a lot easier to move around the list. Okay. And we're not going to actually go through the line editor, but I would say, take some time. A few of you have asked, hey, what can I go through to try to, do better at this? I would say, as an exercise for you, there are approximately 51 slides or 50 slides of stuff talking about this line editor application, and the book actually spends a long time talking about it as well. See if you can create this line editor. Line editor is kind of like a pre-text editor, so it's pretty simple, but they make use of the linked list structure, so you can see how it works. Other projects that they have included in here, such as on page 320, they have an expansion to the SinglyLinkedList. They provide more genuine definitions instead of just empty definitions or throwing exceptions. Okay, and then they talk about making this the SinglyLinkedList circular. That's on page 322. That's interesting too. So that gets some of the benefit of the doubly linked list, where you can go from the last method or last element in the list all the way to the first element very easily by following next, so you don't ever point to null as next. Alright, so that's pretty much all we need for this week. As always, if you have any questions, please feel free to email me, and also you can use the discussion board as well. So I'll talk to you later. Thanks.